All right, we are now going to talk about other rates of change other than the ones that have to do with time. And I think I'm just going to go through an example here so that you see what's going on. The derivative still measures rate of change, but let's look at some questions. So let's say I was working at a factory and the cost of producing a certain number of items, X, in that factory each day is given by this equation right here. Now the first two terms represent cost of labor. The 5x represents the costs of the raw materials, and 2200 would represent your fixed costs, which means I always pay those costs no matter how many items I'm producing. So that would be stuff like rent or mortgage or heating costs or lighting costs, that kind of stuff. So there's your equation for how much it costs to produce that many items, X items, on a particular day. All right. So what we're going to do first is we're asked to find C prime of X. That represents the marginal cost function. So another way of writing that is dc dx. So the change in cost per additional item produced. So for each additional item that I produce, how much more is it going to cost? Basically is what it's saying. So to find the derivative, I just use my same rules as before, and I get the derivative is 0.00039 x squared plus 0.004 x plus 5. That's my marginal cost function. That's how much it costs to produce an additional item. All right. So moving on, part B says find the marginal cost when 150 items are produced. So I remember what my C prime function was. Now I just need to evaluate that at 150. So everywhere there's an X, I'm going to plug in 150. And so that is going to be 0.00039 times 150 squared plus 0.004 times 150 plus 5. And if I calculate that, I get that the cost, or the change in cost, is $14.38. All right, $14.38. So if I've already produced 150 items and I want to see how much my cost would change to produce one more, then it would be $14.38. All right. So there you go. Part C. Let's actually figure out the cost of producing 151 items and subtract the cost of producing 150. That's another way to calculate the actual change in producing that 151st item in my factory. So C151, I'm going to go back to the original cost function, not the derivative here. So that's the cubic function that I started out with. And just to save ourselves some time plugging in, I figure out that the cost of producing 151 items is $3,448.19. And the cost of producing 150 items is about $3,433. And remember, I get these just by plugging these x values into the original function. And 75 cents. And so the difference between those is going to be $14.44. Okay? And if I compare that with what I got in answer B, like I'm asked to, remember in answer B I got 1438, here I get 1444. Basically, it's saying that C prime of 150 is a good estimate. And this example isn't typical because the items are not continuous. I can either produce 150 items or 151 items, but nothing in between. I can't produce 150.5. So it almost makes more sense to figure out how much the 151st item is by doing it this way rather than taking the derivative. But more of your examples are going to be continuous, where it makes more sense to take the derivative. All right? All right, so let's kind of look at what's happening at the graph. Here's the graph right here. And as you look at the 150th item here, if I were to take the slope of the tangent line here, that's pretty much the same as the slope of the secant line that joins these 2 points, if I could draw that a little straighter. But you see that really close up, this looks like a straight line, so the tangent line and the secant line aren't going to be very far off as far as their slope goes. So that's another reason, or that's another way to look at it and see that the derivative actually provided us with a good estimate. All right, so again, if you have any questions, please email me, and we'll talk about this more tomorrow.